Registers are the sequential elements that we use in the majority of circuits. Registers are edge-sensitive sequential elements that are very useful and very easy to characterize. So the most important thing we have to understand is that registers are made using latches. So here we have a positive edge triggered register. A positive edge triggered register will register the value of D on Q on the positive edge of the clock. In all other cases, the output will keep its old value and will be in opaque mode. This means that we see the new value of D only when the clock rises. When the clock is positive, when the clock is 0, and when the clock drops, we do not look at D. Q does not follow D. So registers are made using latches, using something called the master-slave architecture. So the first latch is called the master, and the second latch is called the slave. Now, the two latches are always of the opposite type. So if the first is active low, the second has to be active high, and vice versa. In this case, we are using an active low master latch and an active high slave latch. This will lead to a positive edge triggered register. If you want a negative edge triggered register, you will use a active high master and an active low slave. So one of the most challenging parts about registers is understanding how this connection of latches leads to an edge-sensitive element. Once we understand this, the rest is smooth sailing. So let's look at this graph. Here we have D, the input, and D is changing. So D is changing during the 0 phase of the clock, and again it changes during the 1 phase of the clock. So let's see what's happening. So let's call this value A, this value B, and this value C. So let's see what's happening. We have an internal node called QI. QI is not visible from the outside. It is an internal node to the register. All we can see is Q and D. So when the clock is 0, the master latch is transparent, and therefore D is copied to QI. And therefore, during the 0 phase of the clock, we see A change into B on QI. And so during this phase, we see this kind of change. But during the 1 phase of the clock, QI is opaque to D, and therefore the change into C is not observed on QI. And so this is what's happening during the first period of the clock on the node QI. What's happening on the node Q? During the 0 phase of the clock, the slave latch is in opaque mode. It's keeping its old value. So we say that it is keeping an old value Q old. So during the 0 phase of the clock, it's keeping an old value Q old. On the 1 phase of the clock, Q will take the value of QI. And therefore, on the 1 phase of the clock, Q will take the value B, because the value B is the value on QI. And therefore, the change on QI was moved to Q in the 1 phase of the clock. The change on D was moved to QI in the 0 phase of the clock. The thing is, notice that between D and Q, we do not have any chance of creating a direct connection. This is because when the master latch is transparent, the slave latch is opaque and vice versa. So D and Q are never directly connected. For D to reach Q, D has to move into QI first, and then QI has to move into Q. But D can move to QI only during the 0 phase of the clock. And then QI can move to Q only during the 1 phase of the clock. And therefore, we need a 0 phase of the clock followed by a 1 phase of the clock for D to appear on Q. 0 phase followed by 1 phase means a positive edge. So we see the value of D moving to Q on the positive edge. It has not moved in a single step. It has first moved to QI and then moved to Q. But in effect, if we do not examine the internal node Q, we notice that the value of D that occurred on the positive or rising edge of the clock is the value that appears on Q. Q cannot accept the value of D during the 0 phase of the clock or the 1 phase of the clock because Q cannot see D directly in either phase. During the 0 phase of the clock, the slave latch is opaque and cannot observe D. During the 1 phase of the clock, the master latch is opaque and will not allow D to flow into Q. So now what's happening on the other edge, on the negative edge? On the negative edge, the master latch becomes transparent and the slave latch becomes opaque. And so D has updated to C, but we did not latch this change on QI because Q during the one phase of the clock was opaque. As soon as the clock goes down to 0, C will appear on QI. However, Q will keep B because Q is now, because the slave latch is now opaque, so it will keep its old value. It will only copy the value of C on the upcoming positive edge of the clock, and so we will see C only when we come to the positive edge. Unless, of course, D had updated sometime in the middle to a value D, in which case QI would also update to this value, and in which case the register at Q would be of D. And therefore, we only see registering on the positive edge of the clock. Again, we can also design a negative edge triggered register. We cannot design a register that is active on both edges using simple hardware. Now, how is the register designed on the inside? If we look at the construction on the inside, it is simply made using a master latch, which is this, and a slave latch, which is this. The architecture of each of the latches was discussed in detail in the previous video. We just have a positive feedback structure in each latch. We have a feed-forward structure in each latch. There are two transmission gates, one used to connect D to Q during the transparent phase, one used to connect the positive feedback during the opaque phase. Recall that the switches use transmission gates to allow full logic values to travel, that the inputs to the NMOS and the PMOS and the transmission gate always have to be logic complements of each other, and that also T1 and T2 have to have opposite controls because they cannot both be on, because what they're trying to do is they're trying to prevent contention on this node. Now, this is the node QI, the internal node, which is the input of the slave latch, and the slave latch begins in inverter I4. The construction of the two latches is identical. The only difference is the control signals given to the transmission gates T1 through T4. Now, when we think about timing in sequential circuits, this is a complicated issue because sequential circuits have a clock. When we talked about delay in combinational circuits, it was simple because delay was defined as propagation delay, the amount of time that goes between the inputs changing and the output changing in correspondence. And therefore, we defined it simply as the 50% point to the 50% point, and we found an expression for delay in a combinational circuit. In a sequential element, there are more than two signals. There's not just an input and an output. There's also a clock signal. So we have three signals, and we have to define delay in relation to these three signals. So delay is actually properly defined for a sequential element in relation to the clock. And so there are three delays in which we are interested. A delay between D changing and the clock changing, and this is called setup time. A delay between the clock changing and D changing, again called the hold time, and a delay between the clock changing and Q changing, and this is called TCQ, or T clock to Q. The definition of each is very important, and understanding where each comes from is also very important. So setup time, or T setup, is the minimum amount of time that an input has to change before the active edge of the clock if this change is to be registered properly. So the question is, you have an active edge of the clock. Do you allow D to change exactly at the edge? No, because there's nothing like exact. So, I mean, what if there's some form of phase noise that causes the edge to come a little bit earlier, a little bit late, right? So D has to come before the active edge. How long before the active edge? Setup time before the active edge. If D is ready at the input of the register more than setup time before the active edge, that's fine. If it is ready closer to the active edge than T setup, that is not fine. So what is T hold? T hold is the amount of time we have to hold the data stable at the input of the register after the active edge if the data is to be registered properly. So basically what we are saying is that data has to be held at the input of the register for an amount of time equal to t setup plus t hold. T setup before the active edge and t hold after the active edge. If we obey t setup and t hold, if the data is stable for this window of time around the edge, then Q will appear at the output of the register in response to this value of D. So this will be transferred here after an amount of time equal to TCQ. So TCQ is the amount of time after the active edge that the new value of D is registered at the output of the register. The new value of D is defined in a window around the active edge. Now, normally TCQ is a longer delay than T hold. We will find out why. And therefore, if someone asks us to give a single number as a delay number for the register, that single number would be just a delay between D and Q. This is the closest thing to combinational delay we have. Delay between the input changing here and the output changing here. And so this is the total delay of the register, which would be T setup plus TCQ. However, this single number is extremely useless and extremely misleading because it is not a single delay. The total number does not represent anything. We have to have the input ready, T setup before the clock, and then the output will appear TCQ after the clock. Their summation together means very little until we start to explore pipelines.